We moved on. We're in chapter 3 now, talking about molecules, compounds, and chemical equations. So, what is a compound? Compound is a combination of elements. So, two or more elements can form compounds. And to give you an example of how many different types of compounds there are, so the English language has 26 letters, and you can combine those letters to form different words. And actually can change the nature of the sounds, right? So, T and H and S and H, for instance, combine to form completely different sounds. And likewise, elements can form together. I've used this example before where you can have nickel, which many people are allergic to, but you can combine nickel and titanium, and then you use those in dental um, uh, implements, and then people are no longer allergic to them. So that's just an example biologically. There's many things. So hydrogen and oxygen are both gases, and they come together to form water, which is a liquid, which is completely different from hydrogen and oxygen, completely different properties. So that is an example of how elements can form different types of compounds. And I just mentioned this with hydrogen, oxygen, and water. And here are the data that shows it. And water, yeah, is used to extinguish flame, but it's different types of flames. Water can be used to only Class A fires, which are solid fires. So be careful what you use for water for extinguishing fires. You do not want to put it on a liquid fire, metal fire, or electrical fire. So the different types of fires there. Water works by putting out fires by taking the heat away. Because if you throw it on a campfire, you're the steam, the water turning the steam and taking the heat away from the fire. So mixtures and compounds. So you can form different compounds can come together to form different mixtures, but in this case, the mixture talks about the ratios. So we've already talked about the law of definite proportions in the previous chapter. And we've mentioned this, that there's set ratios of elements for specific compounds. And this is shown here in water, where it's 2 parts elemental hydrogen to 1 part elemental oxygen when it comes for water. And what bonds them together? Why do hydrogen and oxygen form? Well, it's because of the chemical bonds. So the hydrogen now attaches to the oxygen instead of the hydrogens attached to hydrogens and oxygens attached to oxygens. And these chemical bonds, we'll talk about this more in future chapters, but there's a strong intramolecular force, so intra within the molecule, that bind the atoms together. And these types of bonds are either ionic or covalent. And I was thinking about with water, it's covalent. That means a sharing of electrons. Ionic means a transfer of electrons. So ionic bonds, when electrons are transferred from one atom to the other, typically a metal to a nonmetal, but this can be various cases. You can have polyatomic ions that are covalently bonded nonmetals, and the positive ion, which is most typically the metal, becomes the cation, and the anion is typically the nonmetal, or the group of anions, or a group of non-metallic elements become the anion. So if you have a hard time remembering cation and anion, the T is like a plus sign in cation. And now these opposite charges attract via the electrostatic force, and that forms the ionic bond. So solid phase, the ionic bonds tend to form a crystal lattice, and this is a way of describing where the atoms are in space. And it's a three-dimensional structure. And for instance, here you can see this is all in a simple cubic. We're not going to go through too many of the different types of lattices. There's many different structures. It's not all simple cubic. The halite structure, which is sodium chloride, has this. It's a very simple organized pattern there. But the sodium metal reacts with chlorine gas. You can see here sodium metal, and we're not going to talk too much about metallic bonds. Metallic bonds is like a sea of electrons. You have a bunch of positive charges, and the electrons flow in between them almost like a sea of electrons. And chlorine gas here is a diatomic. You have 2 chlorine atoms sharing electrons. And in this case, they react. The sodium atoms give electrons to the chlorine atoms. The sodium ions become the cation. The chlorine atom becomes the chloride anion with a negative charge. And then they form a crystal lattice by the attraction between the positive and negative forces. And something to note here, you can see that when the sodium atom loses an electron, it actually decreases in size. The electron cloud shrinks. And likewise, when the chlorine becomes chloride, the electron cloud expands because of that -1 charge. And the electrons are negatively charged, so adding an negative charge to an already negatively charged region causes it to expand. And covalent bonds, these are with one or more nonmetals. This is not entirely true. Metals can actually covalently bond, and metals can covalently bond with nonmetals, but this is a beginning class, and over the beginning part of the beginning class, so this is not entirely true. But covalent bonds can occur between many different types of metals and nonmetals. So it's just a sharing of electrons. And these sharing electrons are called molecular compounds, so forming a molecule. And I'm not exactly sure what this figure is showing, because there's certainly molecules that have the shapes that they have it there. I guess this is trying to say that it's best when you have the ions in that configuration in the middle, because there are many different types of crystal lattices. So I guess just ignore that picture, to be honest with you. So what type of bond forms between nitrogen and oxygen? This is going to be predominantly covalent because they're both nonmetals. So, and let's move on, talk about chemical formulas. And this indicates the number of elements relative to each other. So if you look at water, you have this H2O. That 2 subscript on the H, that means that there's 2 atoms of hydrogen, and not listed in the oxygen there, but it implies there's 1. That means there's 2 atoms of hydrogen and and 1 oxygen. And NaCl, since it's not listed as, well, there's no subscript listed, so that means that there's 1 sodium, 1 chlorine. Carbon dioxide, you have 1 carbon and 2 oxygens, the 2 on subscript of CO2. And like carbon tetrachloride, and we'll talk about the names later, the tetra means 4, so there's 1 carbon and 4 chlorines. Since there's 1 carbon, it's not listed, but the 4 chlorines are listed there as the subscript 4. And we have different types: empirical formulas, molecular formulas, and structural formulas. So empirical formula gives the relative number of atoms. Molecular formula gives the actual number of atoms. So for hydrogen peroxide, H2O2, that is the molecular formula. The empirical formula here is HO, because it's 1-to-1 ratio hydrogen to oxygen, but there's actually 2 of them, and so on and so forth. So diboron hexahydride there, B2H6, that's going to be that's the molecular formula, but the empirical formula is BH3, the 1 boron, 3 hydrogens. And carbon tetrachloride is already in its the empirical formula, and the molecular formula are the same. Structural formula shows the connectivity to each other and can sometimes show the molecule's geometry. For instance, here, hydrogen peroxide there can be shown this way. And we'll talk about this more later in future chapters, but this is also known as a Fisher diagram. So actually the hydrogens are popping out of the page, and that's going to be at a tetrahedral structure. So that bond angle is going to be slightly close to a tetrahedron, which is 109.5 degrees. But later on, we'll talk about the repulsion. The electron clouds on oxygen are going to push that bond in, so it's going to be slightly less than the perfect tetrahedral bond. But we'll talk about that in future classes. That H2O2 there is not a linear molecule. It's not a straight line. It's actually a bent structure. But again, we will talk about that more later in future chapters. And from this formula, we want to know, we'll see what information we have from it. And the structural formulas tells you the most information. You can see that I was able to talk about the different bond angles and whatnot with the peroxide, which you will learn in this class. You'll be able to do this later on, don't worry. And the empirical formula tells you the least, just the relative amounts. So what is the structural formula for water? C. C is showing you what the structure is in water. I told you before, is the Fisher diagram. Actually, those are popping out. So we'll talk about that in future classes. So a molecular model tells us the most accurate, and we can have the ball and stick model. And I hope you are not colorblind. If you are, we can sort. You can see that they're slightly different sizes, and hopefully these pictures are shown that you can see them properly. But you can see each element is named slightly differently. And you can also have a space filling model. So where the electron cloud is, a space filling model is going to be closest to where the molecules and the force fields around it. So force field, I mean where the electrons are and how they interact with each other in terms of the size of the molecule. So what they are, you can see there with methane. This is all methane, and you have the space filling model is going to be closest to actually the way that the molecule is going to kind of be in nature. At least I mean I know it's a model, it's a representation, but the representation shows where then the electron cloud is, and then that negative charge, how it's going to interact with the surroundings and other molecules. So to give you an example of some of these, so benzene, you can say benzene and acetylene, these both have the empirical formula of one carbon and one hydrogen, but there's a vastly different structure. And there's vastly different properties as well. Benzene's a liquid at room temperature, acetylene is a gas at room temperature, and they have different reactivities. And you can see acetylene has a triple bond, and benzene has an alternating single and double bond. And you have glucose here, and it has the empirical formula CH2O. And so those of you who know that sometimes referred to as sugar as carbs, carbohydrates. Why are they called carbohydrates? Because you can see that glucose is 6 carbons, and then there's 6 H2Os. So that's where the word carbohydrate comes from. It's kind of like a hydrate of carbon. That's not proper usage, but the ratio is where we get the term carbohydrate. But it's not. You can, if you see the molecule here, there's no water in the molecule. It's just but the name has stuck, and there's ammonia. And ammonia, oh, can you see it's actually a pyramid? You can see it's actually a pyramidal structure. So you talk more about that later in future classes. So let's talk about the elements. So elements are pure, well, with the pure substance. Pure substance can be either elements or compounds. They can be atomic or molecular. Frequently, metals are considered atomic, even though they're in a metallic structure. Compounds are typically either, well, they're molecular or ionic. You can have a molecular lattice. So a diamond, for instance, is a well, that would be atomic. That would be an element. So that would be an atomic molecular lattice. But water, for instance, there is a molecular compound, and there's an ionic compound, and there are certain properties of these. I don't want to get into too much now, but molecular compounds tend to have lower melting points. Ionic compounds have very high melting points. Like, have you ever melted sand before, or salt? So I've never melted. Well, I guess I've worked with glass, but that's typically a mixture of sand and various other things like sodium carbonate. But I've never just melted salt before. I've certainly melted water. I do it, well, quite frequently with ice cubes in my drinks. So it's typically relatively easier to melt molecular compounds versus ionic. So, but again, it's teasing for the future. That's what we'll learn about in future classes. So I already mentioned this, atomic elements, and we include metals in this. And molecular elements, they have they are nonmetals typically, and they form structures together. And I know they're not listing carbon. I guess that'd be hard to say because it is a molecular structure and it's atomic. So hey, there's always exceptions to rules, of course. So here is the periodic table. It shows these, and there's various forms too. So you can use phosphorus and sulfur have different forms. Carbon has a couple different forms. The most common is graphite, can also be diamond, but it also has fullerenes, C60, C70. So, and also carbon nanowires, which is actually kind of graphite, but it's interesting. Hey, what's chemistry class unless I contradict myself 5 times in a lecture, right? So what is this? What classifies substance by the molecular view here? Is this an atomic element, molecular compound, or on a compound? So these spheres are all the same color. They're blue. So it's probably nitrogen by the previous um, color code. And there's two of them. So the same element and they're joined together. So this is a molecular element. So molecular compounds, they have two or more covalently bonded nonmetals. And the molecules are composed of their constituent atoms. So here we have water. Well, here's just various ones. We're just saying different compounds. Compounds are combination of elements, two or more different elements. And these are all two elements. You can have much more. Sugar, for instance, has got three: carbon, hydrogen, oxygen. Ionic compounds have cations, or I mentioned this, positively charged ions, usually metal, anions, usually nonmetals, and they're held together by an ionic bond. That's the positive negative charges attraction. And they usually have a formula unit. Well, usually they have a formula unit. That's the simplest ratio. So like NaCl, it means there's one sodium to one chlorine, for instance. And so here are some of the pictures of that. There's propane. So 3 carbons, 8 hydrogens there, looking in that molecule. And then you have sodium chloride has the lattice structure there. And let's summarize this. So ionic compounds are going to have positive, negative ions. And the chemical formula, sum of all the charges of the cations must equal the charge of the anions for a neutral molecule. And the formula of the ionic compound reflects the smallest whole number ratio of the ions. So that's within the ionic compound. So let's talk about names. So we can use a periodic table to predict the charges, and the representative elements, that's the S and P blocks. You know, the furthest to the left and the furthest to the right. Those have one type of charge. Alkalis are +1, alkaline earths are +2, for instance. And the transition metals, some of them have only one. Some have multiple. It really depends. It just depends. So, but they tend to have predictable patterns. So let's name them. The simplest is you say the metal forms the ion, and you just use the metal's name. So that's for type 1. Type 2, you can have more than one ion, and when that happens, we have to say the charge or write the charge. So let's start with the first one is the metal has always the same charge. You just say the metal's name. So here are the elements that only have singular charges. So alkali is always +1, alkaline earth +2. Beryllium does form +2, but beryllium is so toxic we typically don't use it. So scantium there, element 21 +3, zinc +2, silver +1, aluminum +3. So those are the ones that have various sets. So which metal has the same charge of all its compounds? Look at this one here. D, strontium is an alkaline earth. That's a +2 one. So here are the common monatomic ions. So if you're in a monogamous relationship, how many individuals are you seeing? Mono means one. Monatomic, mono is one. That is one atom, one person, mono, right? So the halogens are all -1, oxygen family -2, nitrogen family -3. You can see the trend there with the periodic table, kind of previously mentioned. And we have the base name of that. So fluorine is the elemental name, and then the fluor is the base name, and fluoride, so the plus IDE for all those. So when you have a binary compound with only 2 elements, and this is type 1, meaning that the metal does not change its charge. You just say the metal's name, and then you have the base of the nonmetal, and then plus IDE. So for instance here, KCl, K is potassium, Cl is chlorine, so potassium is +1, the chlorine or chloride is -1. So we just say, we don't say potassium +1, we say potassium, and then the chlorine becomes chlor plus IDE, chloride, so that's potassium chloride. And same thing with calcium oxide or CaO. Calcium metal is not calcium +2, it's just calcium, and then the oxygen becomes oxide, calcium oxide. So what about multiple charges compounds? What we do here is we indicate the charge by either by speech or by Roman numeral numbers with them. So, for instance, iron can be +2 or +3, and copper can be +1 or +2. Other ones too: lead, titanium, tin. Why am I saying? Jeez, tin, lead, titanium, tin. They have various things or various charges. And how do we deal with them? We include the charge in Roman numerals in parentheses, and then it's the same thing as the first one: name of the metal, charge of the metal in Roman numerals, and then the base of it plus IDE. So iron +2 becomes iron 2. Iron +3 becomes iron 3. And Roman numerals I, so you really only have to know this up to really probably 6. I is 1, II is 2, III is 3, IV is 4, that's 1 less than 5. So V is 5, VI is 6. So that's what it is for Roman numerals for the for 1 through 6. And here are some common elements that have various charges. And we don't typically use the older names, so ferrous and ferric. So for instance, we usually say iron 2 and iron 3. So, and there's an old chemistry joke where you put a circle of Fe plus 2s, and you say, what is this? And you say, it's a Ferris wheel. So another, that's one thing about being a chemist. The humor can be tough, right? So, and you can see some of these names. They're actually, well, a lot of them are Latin. So ferrum is the Latin iron, and stannous is the Latin for tin, for instance. And like plumbum is lead, and that's where we get the name plumbing from as well, because plumbing used to be lead pipes, and at least in the Roman Empire times. So, but those are the older names. We don't typically use them anymore, and so let's give an example of one. So, CrBr3, chromium, and 3 bromines. Chromium has a couple of different states. So, how do we tell that? Just looking at this. Bromine is a halogen. So since bromine is a halogen, it's only going to have a -1 charge. So that forces the chromium to be +3. So the whole thing has to be neutral. So since bromine is -1 and there's 3 -1 charges, that means that the chromium needs to be +3. So we say this as chromium 3 bromide, or the Roman numeral 3 for the chromium. And we talked about monatomic ions. Let's talk about polyatomic ions. So poly means any. Mono means one. Poly means many. And poly means 2 or more. So we have specific types of polyatomic ions. So, and here's some examples of those. So when we name them the same way, but we give the polyatomic ions name. So for NaNO2, the sodium, you still use the word sodium, but the NO2 ion, that's nitrite, sodium nitrite. So NaNO2 is sodium nitrite. And that's the stuff they put in like bologna and some sausages. So actually, you want to avoid these. These are mutagens. So here's some common polyatomic ions. You can look at this, and since I'm giving the lecture, you can pause and read some. I guess I'll read the names. So acetate, carbonate, hydrogen carbonate, sometimes referred to as, well, I usually say bicarbonate. Bi in chemistry class means extra hydrogen. So carbonate is CO3, bicarbonate is HCO3. For instance, hydroxide, nitrite, nitrate, chromate, dichromate, phosphate, hydrogen phosphate, dihydrogen phosphate, ammonium, hypochlorite, chlorite, chlorate, perchlorate, permanganate, sulfite, hydrogen sulfite or bisulfite, sulfate, hydrogen sulfate or bisulfate, cyanide, peroxide. So those are the different if you want to hear how they are spoken. So, and oxyions, so there's some naming convention for oxyions. and it's kind of hard because we don't have a one where we start with the 8 and where we start with the ite. So sulfate is SO4 and nitrate is NO3. So these are the oxy ions, and so we don't. I mean, this is something that unfortunately you just kind of have to remember and memorize. So but one less than the 8 is the ite. So if nitrate is NO3, nitrite is NO2, and so sulfate is SO4, SO3 is sulfite. And what about with the halogens? You can have more. So if you have an extra one, you say per. So if chlorate is ClO3, perchlorate extra oxygen is ClO4. And one less than the 8 is the ite, and one less than the ite is hypoite. So ClO minus is hypochlorite. So bleach is sodium hypochlorite, for instance. And let's look at this. Identify the polyatomic ion and charge in each of the compound: potassium nitrite, calcium sulfate, and magnesium nitrate. So potassium nitrate at KNO2, that's the nitrite ion. Calcium sulfate, SO4, that's a sulfate. And magnesium nitrate, NO3 minus, that's the nitrate. And so that's A. I know I'm kind of giving away with just by saying the names. So hydrates are compounds that have water in them, specifically ionic compounds. And I want to be very clear, carbohydrates are not hydrates. So that is a misnomer. But the name has stuck. So every time you say the word carbs or carbohydrates, you are actually being a very bad chemist. But of course, I use carbohydrates, and so it's not proper, but it's in the empirical formula. And so Epsom salts is magnesium sulfate with 7 waters, and the magnesium it's magnesium sulfate hepta for 7, heptahydrate, and so the number 7 for hepta. And cobalt chlorite with 6 waters is cobalt 2 chloride hexahydrates, hexa for the 6. So the hydrate prefixes, so hemi means a half, mono, di is 2, mono is 1, di is 2, tri is 3, tetra 4, penta 5, hexa 6, hepta 7, octa 8. Nona 9, deca 10 is not listed there. So here are some names that you can give with these. And formulas and names, so unlike the ionic compounds, we cannot really determine its constituent elements because there's various things. You can't just say nitrogen oxides. So nitrogen oxides, for instance, look how many different we have. We have nitrogen monoxide, nitrogen dioxide, dinitrogen monoxide, dinitrogen trioxide, dinitrogen tetraoxide, and dinitrogen pentaoxide. So you have various forms. So you have to include it in the name. And so already compounds, of course, first point is always 2 or more elements. So we name the element with the smallest group number first, usually the biggest atom, the smallest group number first. And the same group, right, the element with the greatest row number, so lower down first. So, and the prefixes tell you what atoms are present, unless for the first one you drop mono. So prefix, first one, name first element, prefix plus the second element plus IDE. And we drop mono for the first one if the first element is 1, we just name the first element. Acids, okay, so acids release hydrogen ions. We're going to talk about acids much more in great detail later. We're just going to talk about naming them now. So usually hydrogen is first with the acids. So what are acids? And we're just going to talk about this briefly. Acids taste sour. So, like, if you drink vinegar, what are you going to like? This is sour. And we take a lemon. This is, it's very sour. It's citric acid and lemon. So that's a sour taste. Dissolves many metals. And the metals they don't dissolve are the expensive ones, right? So silver, gold, mercury, platinum, those don't dissolve in acid as readily. And the acids usually start with H. So HCl, hydrochloric acid, H2SO4, sulfuric acid. So, and it breaks apart to form hydrogen ions and anions in water. So let's talk about how we name acids. There's two types. The binary acid has only two elements. The oxyacids that have oxygen in them. So it's binary acids are the easy one. Oxyacids is a little more difficult. So binary acids are easy. You just say hydro, base name of the nonmetal, plus ic plus acid. So very simple. So let me give you a couple of examples. HCl, hydrogen and chlorine. So hydro and then chlorine, chloric acid, hydrochloric acid. HBr, hydrobromic acid. HF, hydrofluoric acid. So that type of thing. Oxyacids, if you have the oxy ion as 8, it becomes ic. If the oxy ion ends in ite, it becomes us. So if it's sulfate, it's sulfuric. If it's sulfite, it's sulfurous. So that's where the names come from with that. And when writing from the acid, if the name ends in acid, it's going to start with an H. If it's ionic, write the formula as if it's ionic, even though it's molecular. So you put H first. And the hydro just means it's an acid. So hydrochloric acid. And I already mentioned this before, the oxyacid. So this is kind of a repeat slide. And so why do we care? Acid rain. So nitrogen oxides and sulfur oxides, these can react with oxygen and water to form further acidic, to form aqueous solutions. And then this can cause damage to plants because if the plant is not used to acid, it can eat away the roots of the plants. It also damages architecture. So here is the nomenclature flow chart. Inorganic meaning not organic, meaning not carbon chemistry. Carbon chemistry we'll talk about in a little bit. So for the simple one, the ionic and metal and non-metal. For the simple ones, and there's only one type of ion, you just say the metal and then the base name plus IDE. So in this case, calcium iodide. For a metal that has more than one type of ion, you name the metal and then the charge of the metal in Roman numerals and then the base of the anion plus IDE. So FeCl3 is iron 3 chloride, and the chlorine is -1 charge, which forces the iron to be a +3 charge. So molecular nonmetals only. The prefix name of the first element, prefix name of the second element plus IDE. You drop mono if the first one is 1. So for instance, P2O5, diphosphorus pentoxide. So di for the phosphorus, penta for the 5, oxygen, oxide. Acids, binary acids, 2 element with hydrogen, use the word hydro, base name of the metal plus ic, plus the word acid, hydrochloric acid for HCl. For oxyacids, if it's an 8, you change it to ic and acid, so phosphate, H3PO4 becomes phosphoric acid, and then if it's an ite, so sulfite, it becomes an us plus acid, so sulfite, H2SO3 becomes sulfurous acid. So, and now we're going to move topics away from nomenclature, talk about formula mass. This is also known as molecular mass or molecular weight, and you sum up the whole parts. So the formula mass is the number of elements in the first element from the chemical formula times the atomic mass of that element, the atomic mass you get from the periodic table, and you add that up, and then you get the formula mass. So H2O, water, you have 2 times the atomic mass of hydrogen plus 1 times the atomic mass of oxygen to get you 18 atomic mass units. So the molar mass of compounds, that is how much the mass of 1 mole of something. And the units we get is grams per mole. So, and we get these from atomic mass. We already talked about water. That means that molar mass, 1 mole of water has 2 moles of hydrogen and 1 mole of oxygen. So and that also means that you have 18.02 grams of water, you have a mole of water, which means you have 6.02 times 10 to the 23rd molecules of water. And showing here, shows a dimensional analysis. This is how you can go from number of molecules from the mass of something. And using the dimensional analysis, the units cancel. So chemical formula, this tells you information here. In combination, it tells you the relative quantities. And we can also look at the mass percentage of things. So if you know the number of a certain element, you can figure out the mass of that element, but then you divide it by the entire mass of that compound. So for instance, we can figure out the relative amount of elements in a specific compound. So, and we can talk about the relationship between them. So, and here with chlorine, with CCl2F2, so this will tell, we can look and say how much chlorine is in this. So if you look at chlorine in the periodic table, it is 35.45, so you can calculate, we can look at it directly here. It tells you that it's 58.64, but you can calculate it out from the periodic table. Carbon is 12, chlorine is 35.45, and fluorine is 19. You can do 35.45 times 2 divided by the quantity 12 plus 2 times 35.45 plus 2 times the quantity 19. So you can do that, and you can also get the mass percent. So molecular formula for water is H2O. What ratio can we correctly derive from this formula? Well, we know that there is 2 moles hydrogen and 1 mole. We know, well, it's going to be by moles, and there's 2 moles hydrogen to 1 mole water. So that's only the volume and the mass is not necessarily information, but we can certainly tell them the ratio of moles. So determine the chemical formula from experimental data, and some homework assignments with this. The empirical formula, it's the smallest whole number ratio. So it's not the masses, it's the number of moles. And you can do this and you can find this in various ways. So how do you do this? If you have percentages, start with grams. I usually just do 100. And if you already have the mass, then just stick in that. So what you do is you have the mass of each element in the compound. You convert that to moles, and so that means you divide the amount that's in the periodic table, right? So if you say you have 10 grams of hydrogen, you divide by 1.008, that's the atomic mass of hydrogen. And then you divide by whatever you have the lowest amount of elements, and you get the smallest whole number ratios. So divide by the smallest number, I jumped ahead. And then for fractions, you get rid of the fractions. So chemistry deals with a branch of mathematics called discrete mathematics. So you only deal with whole numbers. You can't have half an atom. You can only have whole atoms. So if you have a half, multiplied by 2. If you have 0.33 or 0.67, multiplied by 3. If it's a quarter or 0.75, multiplied by 4. So that's how you get rid of those fractional. And if it's a whole number, then you're fine. So the molecular formula, this is the whole number ratio, and it's the smallest one. And the molecular formula, if you're giving some number of units, so let's say you find out that the formula ratio is carbon to hydrogen. If it's 2 units of carbon to hydrogen, then it's going to be C2H2, which is acetylene. If it's 6, it's going to be C6H6, which is benzene, for instance. So, how do you figure out that number? You get the molar mass of that and divide it by the empirical formula molar mass. That'll tell you the number of units of each you have. A common technique, which you don't use anymore, we have much easier ways of figuring out what's in stuff than combustion analysis. But you can do it to figure out what's in for organic chemistry. And this is also some interesting history for oxygen. we had a hard time figuring out what oxygen was. It's because actually, and we originally discovered it because it was missing mass in organic compounds. Like, where is this stuff? Where is this mass going? We're disappearing mass, and it turned out that disappearing mass is oxygen. And then we found out that oxygen wasn't responsible for tarnishing metals too. We thought that there was some magical thing called phlogiston, which is fire that makes metals tarnish and lets things burn. And of course, it turns out it was oxygen, so no longer phlogiston. So, but when we burn things, the carbon forms carbon dioxide, the hydrogen forms water, and the missing mass is oxygen. And from this, you can figure out what's in stuff by burning. And so you burn something here and then absorb the water, and seeing how much water absorbs, and absorb the carbon dioxide, and that will do that. So what's an example of a water absorber? So magnesium sulfate and calcium chloride will do this. Those will absorb things. Carbon dioxide absorber, calcium chloride also will do that, and calcium hydroxide will do that. It depends. I guess you probably wouldn't use calcium chloride then, because it might absorb the carbon dioxide for water. Calcium sulfate's pretty good for that too. Or silica. Silica can do that too. So there's various things that will absorb water and carbon dioxide. So, and this is, again, history. Chemistry used to be organic and inorganic. Organic was thought to be living. It had the life force. We called it elan vital. And so it sucked the life out of me. That's suck this life living force out of me. There's no such thing as that, of course. So things from living things were considered organic. Things from non-living things like the earth were considered inorganic. And they were having an easy time synthesizing inorganic things, but not so easy time organic. And of course, we're much better this day and age. But today, organic compounds, we can do them. We can make them much more easily. And organic compounds are typically made of carbon and hydrogen, but we can also have oxygen, nitrogen, sometimes phosphorus, sometimes sulfur. So they're found. So nucleic acids and proteins, for instance, can have phosphorus and sulfur in them. But the key for organic chemistry is carbon. And we're going to talk about organic chemistry in much greater detail later on. But carb atoms, they tend to be very covalent. They can form polyatomic ions and then ionic bond, but carbon really tends to be much more covalently and than ionic. And carbon can form 4 bonds, which include single, double, triple bonds. And there are many things that are weird about carbon. And of these, I think the most unique is the fact that it forms straight chain bonds. So all of these structures that we have in life, they're all straight chained. And that's very weird. That is the strangest thing about about atomic carbon, is it forms these straight chains of things. We'll talk about this more later. I could talk forever on this. I could talk like it's my job, which is my job, but you're probably getting bored on this lecture by now. So here are some examples of carbon bonding. You can see that they can have straight chain. It's only 3, so I guess they can't really have straight chain, but it has single, double, triple bonds. It can have ring structures. It can bond with other elements too, and tends to have 4 bonds. So it's really interesting, and these molecules are all very different as well. So hydrocarbons, and we're going to cover this in much greater detail in future chapters. So organic compounds tend to have hydrocarbons. So like a Celebrity Jeopardy question, the easy Jeopardy. What 2 elements in hydrocarbons? Hydrogen and carbon. So I know I didn't give you enough time to guess. I'm sorry. But hydrocarbons, hydrogen and carbon only, and then we can have some groups on them to give that. And the hydrocarbons, very common. So fuels, we use hydrocarbons quite a bit for fuel as well. And oil, you can use oil also in your engine as a lubricant. We have other uses for hydrocarbons. It's not exclusively fuels, right? We asphalt on the roads and that kind of tar for, like the roofs and whatnot. So those are hydrocarbons as well. And they burn. They will burn. So when you name them, and again, this is just the brief overview, but single bonds only, also called saturated, these are known as alkanes. And if you have a double bond, it's alkene, and a triple bond, alkyne. And so, and then we have the number for the hydrocarbons listed, and so for uh, one carbon, the meth, 2 ethyl or eth, 3 prop, 4 buta, 5 pent or penta, 6 hex, 7 hept, 8 oct, 9 non, 10 dec. And so, for instance, here, let's name them: 1 carbon methane, 2 propane. I'm sorry, 1 carbon meth, 2 is ethane. Jeez, we're skipping 2. 2 is ethane, 3 is propane, 4 butane, and it says N. The N means normal, which means a straight chain. Pentane, so normal pentane there, straight chained. Ethene and ethyne, so the two carb, like instead of ethane, ethene, ethyne. So that's how you say the alkene, the double bond, and ethyne, usually called acetylene. So ethene, a lot of times called ethylene. Ethyne is typically called acetylene. So, but those are more common names. And the functionalized group, these are something attached to the hydrocarbon, and then it changes the properties of them. We organize them by functional group. For instance, the OH is an alcohol. So you have the methyl group, and then the OH, so this is methanol or methyl alcohol, and isopropyl alcohol here, also known as 2-propanol, is a more proper term. So that's a functional group. And these are the families of organic molecules. Alcohols have the OH group. Ethers have an alkene attached, 2 alkenes attached to an oxygen in the center. Aldehydes have the terminal C double bond O H group. The ketones have a C double bond O in the center with 2 same or different alkyl groups. That's the alkyl means hydrocarbon. Carboxylic acid has that C double bond OOH terminal group. Ester is just like a carboxylic acid, but instead of a hydrogen, it has another alkane attached to it. And then amines are like ammonia. Ammonia is NH3 that has 1 or more different alkyl group to it. And these are some of the things. And that's something about chemistry. It can smell wonderful, and it can smell really bad. So you can get the smell of rotten fish, and you can also get some really great things. Esters tend to smell really good. Ketones can smell really good too. I don't like acetone. That smells bad, but some other ones smell really good. Same thing with aldehydes. And we're done. Don't worry, there's much more organic chemistry later on, but we're just kind of doing the quick overview there. So